Hello, today I will be talking about a better decision through science. First, the many applications that are visible on better decision through science are a wide range. They can be from healthcare, public safety, business environment, justice, education, and many others. It is quite important because sometimes the decisions that have to be made are quite critical, and therefore a solid ground either by theory or by expertise of either a doctor or an engineer, it's greatly required in order to have the best decision possible. Since there is a wide range of fields where this decision making through science can be applied, the method it's quite vast and quite helpful, but it's not well and or widely known. So it's a good option to get to know this method in order to apply it to any of our fields of expertise. First, we need to have some terminology in order to get a better grasp on the actual topic. We have four concepts that we will be learning its real definition, the book definition. But on the following example, we will understand a little bit better about this concept. But maybe in actual paper or by reading just a description will not be as clear. First, we have the true positives. The true positives are also called hits. They are the percent of individuals who truly have the condition in question and will correctly be deemed to have it. We will explain in deeper detail about this and the other concepts. We also have the false positives that are also called false alarms. These are the percent of individuals free of the condition that will mistakenly be deemed to have it. Then we have the negatives. We have also the true negative and the false negative. The true negative, it's also called a correct rejection. It's the individuals that are correctly deemed to be free of the condition being evaluated. And finally, the false negatives, they are also called miss. And they are individuals that are incorrectly deemed to be free of the condition. So these four concepts may not say a lot on just reading words, but on the next plot, on the next graphic, we can have a better grasp on these concepts. So if we plot them in the matrix in an actual table, then we can see on the x-axis we have the actual value. That means that it's the real value and not the value we say or we think it is at the beginning of the exercise. Then on the y-axis we have the prediction outcome. The prediction outcome is the decision that we will state as some individuals. In this case, we're gonna analyze a patient's situation. Then, if they are, if they or they have or they don't have a certain disease. For instance, I'm gonna explain this a little bit better. If we predict that a patient has a certain disease, and in the long run it turns out that actually this patient has a disease, then we have a true positive. But for instance, if we say that the patient has the actual disease, but in the real life the patient doesn't have it, then we're talking about a false positive because it doesn't have the disease. Then we can have the prediction. If we say that they don't have the disease but they actually have it, then it's called a false negative. And finally, if we say that they don't have the disease and they actually don't have it in real life, then we're talking about the true negative. So we can say from this matrix that the positions where either the interjection of p's, the prediction, and the actual values, if they are the same, for instance p and p, then it's a true positive, meaning that we actually hit the target or we actually were right on our prediction. Also, if we say that the prediction that we state that the patient doesn't have the disease, and in real life he or she doesn't have it, then we are also calling a true negative. So the common denominator here will be as the word true, because true means that we actually had the correct prediction. If we don't have the correct prediction, then we call it the false, and it could be either negative, meaning that they don't have the condition, in this case they don't have the disease, or positive, meaning that we were wrong, but the actual condition took place. Then we have the totals on this column, and means that they have the positive or the negative prediction, or the positive or the negative actual value. So we can see in this plot how all these four terms come into place. Then we have the ROC curves. Well, these plots, plain and simple, are helpful in order to see graphically the concepts we just saw in the previous matrix, in the previous table. ROC curves. ROC means the receiver operating characteristic, and pretty much this curve determines which statistical prediction rule are most accurate if more than one is present. We will see the example later on, just as we did with the terminology. Also, the ROC curve, it is known as the graphical plot of the sensitivity or true positive rate versus the false positive rate for binary classifier system. A binary classifier system means that it's just there are just two options, meaning in this case that we're going to talk about either a patient that they don't have the patients don't have the disease, or maybe they do have it. So those are the two options. That's why it's called binary. These curves are based on the overall accuracy of a prediction rule. And lastly, just a little bit of history with this terminology. The ROC curves were first applied in World War II in order to distinguish random interference, pretty much noise, from signals indicating an enemy plane. So how do we build an ROC curve? Well, for our example, we're gonna talk about patients who have or don't have a certain disease. In this case, glaucoma. So as the description states here, first we need to find a large sample population of people whose eye pressure level and glaucoma status are known. So we can see from the plot that is shown here on the left side of the screen, we have the x-axis and we have the eye pressure reading that it goes from 0 to 50. And we have two plots. We have two curves. We have a blue curve that it means it states the people that are healthy, and we have a second curve, a red one, that states how many people have glaucoma. We have on the y-axis the number having each score. So we can see here on these plots they overlap to each other, and they overlap from the range to 10 to 40, meaning that in this area from 10 to 40 there are some people that either are healthy or other people have glaucoma, but they overlap, so we cannot state exactly how many people are actually healthy or how many people are not. If we pay attention to this plot, we can see on the far left side we see that there's some portion of the blue curve which doesn't overlap with the red one, meaning that all people are healthy beneath this curve, this blue curve here. And then on the other hand, we have on the right hand side of the curve, the red curve doesn't overlap with the blue one, meaning that all people that are beyond 40 on the eye pressure reading have glaucoma. And this is the start of the curve. So we have the binary conditions, so we have either people that have or don't have a certain disease, in this case the glaucoma. So when moving to the next slide, we can see here how we divided the two curves and we actually plotted separately, one on top of the other. This is important so we can have a better knowledge of how much people are either on the glaucoma group, that it's on the top graphic, or it's a person